Hello everyone, my name is Numair, and in this video I will be talking about our work on input splitting for cloud-based SAST platforms. As development teams adopt DevSecOps practices, there is a growing demand for easy-to-use cloud-based SAST platforms that provide a simple interface through which developers submit their code and receive recommendations on how to improve their code. Internally, such platforms may employ a variety of static analysis tools. These individual analysis tools are containerized and instantiated on demand on cloud-based machines. Developers expect such a platform to handle input code bases of arbitrary size and still deliver results within a certain time window. To maintain a predictable response time, these platforms face the challenge that they need to be able to scale to different sizes of inputs, and that every time they add new analysis tool, they have to ensure that the new tool does not slow down the response time for existing customers. In the cloud, a large number of small machines is significantly less expensive than a small number of high-performance machines. Moreover, since many analysis tools in SAST platforms have superlinear time complexity, even the most powerful machines will eventually not suffice. In this paper, we present an approach to horizontally scale analysis tools in a static analysis platform. Our approach takes as input a program and employs a configurable splitting strategy to split the program into partitions such that the amount of code in each partition is below a provided bound. The different pieces can then be analyzed on parallel cloud instances of a given analysis tool. We implemented two different partitioning strategies. Our aim is to distribute the analysis of a program by splitting the program into a number of partitions that can be analyzed independently with the target analysis tools, where each partition contains no more than S files. The first strategy, called size limiting, is a naive splitting strategy that splits the input program containing a number of files into partitions based on an upper bound on the number of files per partition. To ensure determinism, the files are first sorted in a lexicographical order with respect to their names and added to a partition until the bound S is reached, and then a new partition is started. In this example, for S equals 6, size limiting will produce 3 partitions. The second strategy, called SplitMerge, uses dependency information between the files of the input program to create partitions that include the necessary dependencies of a file. We motivate the need for splitting and smart splitting strategies using a simplified version of a test in the OWASP benchmark, which is a standard benchmark for Java SAST tools. This test contains a path traversal vulnerability and calls a helper method doSomething in class thing1. Thing1 is one of the 162 helper classes that are used by multiple test cases in OWASP. The method doSomething is called by a total of 347 tests in the benchmark. Suppose the available compute instances allow a certain tool to analyze up to 100 files before it risks exceeding the SLA time limit. This means we must split the OWASP benchmark into a set of partitions, each of them of size at most 100. First, let's discuss the naive splitting strategy, size limiting, which splits the code base into non-overlapping subsets. For the OWASP benchmarks with a total of 2,902 files, this will produce 29 partitions of size 100 and 1 partition of size 2, so 30 partitions in total. In the previous example, the method doSomething in class thing1.java is called by 341 tests. We know that these tests will be distributed over at least 4 partitions, and only one partition will have access to the implementation of doSomething when running the static analysis. Depending on the analysis tool and its assumption on missing methods, this may result in a loss of findings if the analysis under-approximate, or it may lead to false positives if the analysis over-approximates, or it may even crash the tool. For this example, we need a splitting strategy that is able to create overlapping partitions to reduce the number of unavailable code dependencies in each partition. We therefore introduce a smarter splitting strategy called SplitMerge and evaluates its effect on the number of findings compared to the naive strategy and to no splitting at all. In general, in SplitMerge, partitions are not required to be disjoint. That is, the same file may be replicated across multiple ones. SplitMerge consists of 3 steps. We explain these steps with the help of a small example. Consider a program P with 6 files and a file dependency structure shown in this dependency graph. A directed edge from a file D to B denotes that D depends on B. Such dependencies can typically be computed statically using tools such as JTabs for Java or Snakefoot for Python. In step 1, a partition is created for each file in the codebase. This partition includes the file itself and its transitive dependencies up to a distance k in the dependency graph. For k equals 1, the initial partition will only include the direct dependencies for each file. For example, A, C, D, and F for file E. The distance k is a parameter of SplitMerge that allows the trade-off between the size versus the degree of self-containment in the initial partitions. For k equals 2, the dependency relation is augmented with the transitive dependencies shown in red, and the resulting partitions will include C and B for partitions created for files A and E respectively. A large value of k makes the algorithm more conservative in preserving dependency information. Step 2 aims at splitting an oversized partition into smaller sets that fit within the size limit, since some initial partitions may have size larger than the maximum S. This is especially likely for larger values of the neighborhood radius k. However, uniformly splitting a partition into the minimum number or necessary disjoint subsets is likely to delete dependency information. Instead, we deliberately produce a non-minimal number of subsets, allowing redundancy to preserve dependency information. In particular, for a partition that exceeds the maximum size, we sort the vertices in descending order of degree. Degree of a vertex is the number of its incoming and outgoing edges in the dependency graph, which is 5 for E, 4 for B and C, and so on. We then divide this partition into two sets of vertices, namely high degree vertices and low degree vertices. The low degree vertices set is then partitioned uniformly into small enough subsets to allow adding each such subset with high degree vertices. In this way, we split the oversized initial partitions from step 1 into partitions of acceptable size while maintaining as much dependency information as possible in a partition. The last step of SplitMerge reduces the redundancy introduced by the previous steps and computes the final partition. Some partitions computed by the first two steps may be subsumed by others. For example, the second partition is completely subsumed by the first partition. In these situations, the information contained in the larger set subsumes information in any of its subset. The subsets can therefore be discarded without loss of information. We evaluated the effectiveness of our approach with 3 industrial analysis tools on a portfolio of Java and open source Python benchmarks. Rapid is a static analysis tool developed at AWS that performs IFDS IDE-based type state analysis to detect incorrect usage of cloud service APIs. Infer is a tool developed at Meta that uses separation logic to detect memory-related issues. And Bandit is a tool to find common security issues in Python. OWASP and Juliet are well-known Java benchmarks designed to evaluate automated software vulnerability detection tools. We also sampled 138 large open-source Java benchmarks from Maven Central. Our evaluation revolved around 3 research questions. For the first question, namely, what is the impact of splitting a program and analyzing the partitions in isolation on a tool's accuracy, we found out that splitting the original program can sometimes negatively impact a tool's accuracy, as seen by the reduced number of findings compared to our baseline experiment with no splitting and unlimited time. However, our experiments show that smarter splitting strategies like SplitMerge can controllably reduce accuracy loss. For very large code bases like Juliet and strict resource constraints, splitting may be the only option if we want to retrieve any findings, since the tools do not scale and thus end up returning no findings at all. Splitting the code base allows us to analyze the partitions in parallel. For our second research question, namely, how do static analyzers perform on the partitions compared to the original program in terms of time and memory usage, our experiments show that on all 3 benchmarks, splitting significantly reduced the latency for both analysis tools. Splitting also significantly reduced the memory required to analyze the benchmark suites compared to no splitting. For our third research question, namely, what kind of static analysis tools would benefit from splitting strategies presented in the paper, our experiments show that splitting is useful to limit the per-machine resource consumption of static analysis tools, and different tools require different splitting strategies. Interprocedural analysis benefit the most from splitting, even with a naive strategy like size limiting. For example, splitting the input code base allowed Rapid to analyze code much faster than without splitting. Whereas for Infer, the most prominent benefit of splitting was the reduction in memory usage. Our experiments also show that for inexpensive linter-like or intra-procedural analysis such as banded, size limiting may be more beneficial than dependency-guided splitting strategy like SplitMerge. In conclusion, in this paper, we motivate why splitting is a relevant problem for SAST platforms and why additional research in this area is required. We present experimental results that input splitting can work in practice with different SAST tools. We show that with the proper selection of splitting strategy, all evaluated SAST tools can benefit from splitting. Yet, finding the right splitting strategy depends on the complexity of the used SAST tool. Thank you very much for your attention.